welcome to the seminar or workshop of Introduction to Regression in R. The slides of the workshop can be reached from this link. In this seminar, we are covering the seminar in 3 separated slides. First, we talked about regression model and how to run the regression model in R. In second slide, we talk about the regression diagnostic and how we can detect the problem in regression assumptions. And then in the last part, briefly, we talk about regression with categorical predictors. The data for this seminar can be accessed from this link. Is a school performance and some other variable for 400 sample elementary schools from California. This is part of a bigger data set, which called California Department of Education API, Academic Performance 2000. If you want to get the data, you can right-click on this link and then save the link as an Excel file. It's somewhere in your computer, so you can just save it. I already saved in a folder in my desktop. You can do that, and you can read the data into R. Or you can use the link and then use the link directly in R, and R is able to read the data online. So we will see that shortly. The code for the seminar, you can get it from here. If you click on this link, you can copy paste it into R, or again, you can right click and save it, and it's going to be saved as .R code. So you can save it as, so this is the name of the file. This is the updated. And for this seminar, we are going to use R, and we are using R through the interface called RStudio. You can download and install both R and RStudio. I'm sure that most of you are familiar with R and RStudio, and hopefully you have it installed in your computer, so you can follow the seminar. We are going to give, I'm going to give you a little time so you can copy paste and run the code by yourself, so you get a little familiar with the R environment or RStudio environment. If you want to know more about R, for this seminar, basically, we don't really need the expertise in R. This can be just a startup using R. But if you want to know more about R, you can click on this link, and there is a great seminar as introduction to R seminar. Also, there is other seminars in R. You can go to the software R, click here, and you can access to other seminars in R particularly. So with that, if you click on this, you can get to the seminar page. Because we might have the website down, I'm going to use the local. I'm going to start with this, but there is the link here. If you have any question throughout the seminar, you can use the chat, ask question. Johnny, Lynn, and Andy, Lynn are going to answer your questions in the chat, so you can use the chat to answer your question. Please make sure your question is relevant to the seminar that we are talking about and the material that we are talking today. So everybody can actually understand your question. After the seminar, we will have a discussion and you can answer a broader question, you can answer more question. You can unmute yourself and ask question and we will discuss that questions. Okay, so in this seminar, actually, the first part of the seminar, I'm going to go over the regression model in this part. So first I start with simple linear regression. Then we go over some examples and open the data in R and gets a little familiar with R. With a basically similar to a real data that you might get. And then we run our first linear model and we extract the result of the linear model and very briefly. And then we go over multiple regression. And then we go after that to the second part, which is regression diagnostic. This seminar is going to be recorded. When we get the recording ready and have the closed captioning ready for you, we will post it to our YouTube channel, which has several other past seminars is going to be there too. We just started recording our seminars, so there are not many seminars available yet to the YouTube, but hopefully in future we will have more seminars available for you to follow. Okay, so with that, let's start with our regression model. So basically, what is the regression model? The regression model is a statistical method to explain relationship between a response variable with one or more than one predictor or independent variables. So in regression model base, we start with one variable as response. But we can have one or many predictors. The predictors could be any type of variable. For now, for simple linear regression, we assume we have only one response and one predictor. For example, efficiency may be related to the training, so the amount of training or educational background or age of employee, or the amount of time until a headache is gone. Might be depends on the dosage of the medication that individuals use, and might be depends on also the age or gender. Or for example, number of votes for presidential candidate for each city may be related to candidates' gender, city's average income, and the estate. For example, if the state is east or west as a categorical label. In our example, in today's seminar, for example, we want to see how the academic performance of a student is related to a student poverty level, or how it's related to the number of students enrolled in the school, or how is related to percent of teacher, what percentage of teachers in the school who have the credential, or number of students in each class on average. So if you look at each of these examples, we have some cases or some object, and we have some variables. One response variable, and you can have one or many predictor variables. Simple regression it should be simple regression. It's a study of single response as a function of single predictor. So there is a misspelling. It's simple regression sometimes, or a regression model with one predictor. In that model, we have, for example, X for observation number 1 or person number 1, or for a school number 1, a school number 2, to a school number. So we have n observation of predictor and n observation of response variable. So as you see, we have the data is like a pair. You have X and Y for each person or each object of the study. In linear regression model, we assume this relationship to be linear. Okay, so the regression model can explain only linear relationship between these two variables. But if you want to, later you see, we are not going to cover the quadratic form in this seminar, but you can create a quadratic form of the variable, or you can use a transform function of the predictor and then look at that relationship between the linear relationship between that variable or variables to the outcome variable. But everything starts with their first linear simple regression. By the way, this slide is a slide HTML. If you want to be able to have more access to this slide, I show you a quick. So if you click on H, you will see this. This is a slideshow. So here it says, for example, if you use F, you can switch off and on to the bottom of a status line. Key is when you want to, I recommend to use the key. So going back here, if you use K, the mouse is going to be disabled. So it's easier for you to copy a line of the code and paste it into the R if you want to run it. If you want to make it bigger, you can click on B. It makes it bigger. Or S makes it smaller. Hopefully this is good enough, big enough. I can make it bigger if you like. But I think it's good. So going to the next page. So now you can go with the page down to the next page. So starting before you start the regression model and statistics, let's look at the linear algebra. And we look at the linear function and characteristics of a linear function. A linear function is defined by a slope and intercept. So looks like this. Y is equal to f of x is a function of x, has an intercept part, which is this is intercept in this model is 1, and the slope is the part that is multiplied by x. So you have the coefficient, which is a slope. We have a constant value, which is intercept. If we know these two parts, we know the line, right? We can draw the line. So what is the intercept? Intercept is basically when you replace x with 0, you get the y equal to intercept. So is the value of y when x is equal to 0. That's the intercept. The slope is amount of increase of y for 1 unit increase of x. So this is important later when we want to interpret the result of regression model. So the slope of the line is increase in y for 1 unit increase in x. Or if the slope is negative, is decrease in y for 1 unit increase in x. So always we think of x as increase 1 unit in x, and this value is constant. So if you look at this point also the slope is the same as the slope at this point. So a slope is constant, right? So that's a because it's linear relationship. But in real data, things are not perfect like this, right? So you have the data, and then there is a variation. Then you want to see that linear relationship, but there is always noise, right? So we can model that data using the linear relationship, but we always have a noise part or error part left. So in a simple regression model, we have two parts. There is a part that can be explained by the model and is fixed, is not random. And there is a part, let me just use this annotation, maybe it's better. So, so this part is the fixed part, okay, and this is the random part, right? So there is a fixed part in the model, which is the linear part, and there is the error part. That variation in y comes from this error part in the linear model. Basically, we say that the expected value of y or mean of y given x is equal to this linear part, can be explained by this part. So the mean function is linear and it's fixed, right? But there is a variance here. The error term in regression model assumed to have 0 mean. So the mean or average of this error part is 0. But the variance is constant and is sigma squared. But is unknown. We don't observe this. This is the parameter of the model. And this is also beta 0 intercept is the parameter of the model. Beta 1 is the parameter of the model. All right. I'm sure lots of you have heard about the normality assumption, because in a stat consulting, lots of time people come and ask how we can check the normality assumption in the regression. The normality is not necessarily in the regression model, but if you want to do the test statistics and to have a valid test statistics, normality is important. Usually we assume the error has normal distribution, but the equality of the variance is very important. The most important part is error has mean equal to 0 for every given value of x. So what that means in more detail, we will discuss that. In a linear regression model, the data is like a pair, right? You have xi and you have yi for every participant in that survey or in that data. So for every object in the study, you have a pair of observation. So for example, in our example, for each school, this index is a school 1 to n. If you observe n school, if you have observation of, for example, 100 school or 200 or 400 school in this data, we have a school performance for each school and, for example, number of enrolled students for each school. And for example, if we want to see, this is the relationship between this y value from this x value, this is our y observed, and this is the x values based on the data. So the first thing in the regression is to basically visually see how this relationship is. So we use a plot that calls a scatter plot. Basically, it's a two-dimensional plot of the x in x-axis and y in y-axis. We will see that how we do that, this kind of plot in R. But for now, if we plot that, the points are going to be like this. Let me make this slide a little bigger. Oh, picture is not that big. So the goal of regression analysis is to fit the line that fit the best to this data. So if I have another line here, it's not a good line because all the data are going to, for example, if I have this line, if I draw, let me draw a line here. This is very bad, right? It's far away from all data. This line also might be, but it doesn't explain the relationship. You see that as enroll increases, the number of API score or performance score in 2000 decreases, right? Which line is the best line? That's what we need to find out, right? We need to estimate this line. Again, we said a line is known if we know the intercept and a slope. So basically, we need to estimate the intercept and the slope of the model. So again, in order to have unbiased estimation for the model parameter, the necessary assumption is that the mean of error term to be equal to 0. That's the only assumption you need, that to have the estimation that we will talk about this right now to be unbiased. The method to achieve that baseline calls ordinary least square model. In ordinary least square model, in general, we have this assumption. An error have a mean equal to 0. Error must be independent. Error have equal variance. Errors follow normal distribution. And the relationship of dependent variable with independent variable is linear. So this last one is kind of embedded in the first one. So if the error have the mean equal to 0, we'll somehow confirm this assumption. But this is also part of the assumption of the model. Usually this is obvious that we want to fit a line to the data. Some of these assumptions are more important than the other assumptions. We will discuss the diagnostics of this assumption later in this seminar. So let's say we estimate that beta 0 and beta 1 using the method which is like a black box. We use that black box, put the data there, we estimate these two parameters. After we estimate, we can predict y using the model. Basically, we are the prediction is that fixed part, right? So we predict beta 0, we estimate beta 0, we estimate beta 1. When we put hat, usually in a statistic over a parameter, means that is the estimated value of that parameter. This estimated value depends on the data we have, right? That 100 or 200 data, if we change that, these estimated values will be different. For each observation I, then the predicted value is going to be yi hat. Okay, so yi hat is the predicted value for observation I. The difference between observed value of yi and yi hat is called residual of the model. So this is not the error, it's the residual. It's basically some sort of estimation of that error, right? So this could be positive or negative. Depends on the yi is bigger or smaller than yi hat. In ordinary least square, we find that beta 0 and beta 1 hat in a way that this quantity is minimized. So we minimize this to get these two values, beta 1 hat, beta 0 hat, and beta 1 hat. So there is a note here, the predicted variable may be continuous, meaning that is within a range, for example, height or weight, or age. Or it might be 0 and 1, or it might be categorical variable with many categories. But the outcome variable assumed to be continuous in regression model. Okay, we treat the outcome always as a continuous. Okay, now let's talk about this error part in more detail in next slide. Okay, we talk about this right here. Now, let's have a model without any predictors. We don't have any predictor. How we basically estimate that model? So is y equal to beta 0? If we don't have any predictor, we don't have a slope. So we basically can estimate y using the average, right? Naturally, you can just average all the value of API, for example, to get the average, right? So let's look at this picture, for example. So here, let's say we want to predict this and we don't have any predictor. The most natural way to predict y is using y bar or a line without any slope, right? Now, if we add a predictor, for example, here, we have number of enrolled students, we can do better than this line, right? We can predict it using this line, right? This regression line that predict the value of API score for a given value of enrollment. In least square, basically what we do is we want the difference between the point observed value and then predicted value, which is this point, a square, and add over all these data points to be minimized. So basically this line that I draw here is minimizing all the differences between the point and the line, a square, right? So a square, because there are some negative and some positive, right? This is positive. yi is bigger than yi hat, so this is the positive error. Here, error is negative. If I add all of them, eventually adding all this error, you get 0, exactly 0, right? This is one of the properties of regression model. you get the sum of these residuals, because we call this residual, right? yi minus yi hat. The sum of this residual is 0, but sum of a square is minimized among every line that we drop here. We can extract this difference between yi and y bar by two parts, this part and this part, right? So basically, we can separate this difference between yi and y bar by a part that is explained by the line. This part is the part that line explain the error, right? This line explain this error from this y bar, the model without any predictor. API explain this part, the red one, and there is this part that is remain. We cannot explain it anymore, right? This part. This part is unexplained part. If we square each part of this equation, eventually we get this is true, right? We can show mathematically sum of a square total, we call it, is equal to sum of a square that is not going to be explained by the model and the sum of a square that is explained by the model. So this is sum of a square of all these reds. This is sum of a square of all these blue, which we call also sum of a square residual. The goal of regression model is to minimize this part, right? If this part is minimized, this line is going to be explain the error the most. So we can write it as this equation. This is sum of a square total. This is, we call it residual sum of a square. And this one is sum of a square of regression. And we can calculate R square of the model using sum of a square of regression. This is the portion of total sum of a square that can be explained by the line, right? We call it R square. So the R square that you here in any statistical model is the amount of error that the model can explain. Because total sum of a square is always bigger than this, the R square is always between 0 and 1. So if the model is not useful at all, like this one, right? For this model, sum of a square, the R square is basically 1. I'm sorry, 0, because this part is 0, right? And you can also write it as 1 minus error sum of a square, or residual sum of a square, or sum of a square error, sometimes in some text they use, divided by sum of a square total, right? So when you don't have any predictor in the model. So this is true for simple regression model and for multiple regression model. So the same formula is correct for any regression model. It doesn't depend on if you have one predictor or more than one predictor. Because if you have more than one predictor, still you have y hat, right, as the predicted value using all those predictors. We will see that later in this. Any questions so far? I'm going to pause a little bit here to see if anybody have a question. No question? Okay. So we continue. I know this part is a little like mathematics, and you might not really comfortable with that, it's boring, but this is base, you know, like we need to know at least what's going on here, or at least what is this linear, you know, like this basic algebra. So one predictor and multiple response variable. So that's different. So if you have one predictor, multiple response variable, you have to run separate regression model for each of the response. That's one way to solve that problem. Okay. Or you can run it as multiple regression models simultaneously. So that's a little more advanced analysis, but the base this is basic regression, introduction to regression class. So in regression class, we always have one response variable. Yeah, or multivariate regression. Yeah, exactly. Thank you, Andy. So let me make it a little smaller, maybe too big. So exploring the data. In any statistical analysis, first we need to look at the data. Look at some descriptive statistical model, some plot, some summary statistics. And before that, we need to read the data, right? That's the most important. If you cannot read the data in a software, then basically you have to just sit there and do nothing, right? So the first most important part is how to read the data, right? Before going over that, reading the data, I'm going to introduce you a little bit about R. So when you open R, you see something like this. For this part, I'm going to switch to R, basically. I'm going to open R. Hopefully you see R here. Okay, so if for the first time you open R, you see something like this, right? There is nothing there. You see some, basically, you don't have anything here, let's say. And you have just a console open, right? So now you can go ahead and you can have a new R script like this. So this is my first R script. This is R editor. I can type here and run the code here. For example, I can say X is equal to 1, sorry, equal to 1, and then I can use Control Enter and run this code. You can copy this code and paste it here and run it directly from console, which is not really recommended unless you want to see something where you don't want, not permanent, you don't want to save that code. You want to just, for example, use the help file or do some calculation. What is 4 plus 3.5, for example, right? So you can do that right here, and you don't want to save this result. Although this result will be saved in the history. If you look at the history, everything is going to be here, okay? So if you clear the history, then history is gone now, right? So you see another panel here. You have environment, which is, you can see the variable, and then you can see all the packages, right? And the history here. And there is another panel here. You can see the plot, packages. You can navigate files, right? And that's a basic R study environment, which is cool, which is very helpful sometimes. And then allowing that you work with R, you will learn more, or you might know more than me in this sense, right? So some of you might know R more than me. So let's start with the new R script. I can go to the website actually, and let me see. This was the local I can basically go to this first website and copy paste the code into R here. So if I go to the course website, classes and seminar, introduction to R, I can, the code for the seminar is, okay. Oh, I cannot click. You can copy these. If I click on this, I can copy all these codes. And I can save it in R here, right? Or if you already saved the file, you can open the R code wherever you save the file, and then you can just open the file here. Right? This is how you open the file for this seminar here. So here we can run the code. So to read the file, you can either type a function, read CSV, and read the data from the website. You can read it from a local directory like this, or you can do this. You can go to import dataset, read it from a text, this one, for example, and then click on this, and then find the file here. I'm not going to over this, but you can always do that. You can read the data from SPSS, SAS, data, all these different format, and read it into R. So that's really, really helpful. So if you just run this part or copy paste it from the slide, not here, you can copy paste it from here to the R, and then you can run it. So this way, the data is going to be read from this page and will be stored in a D. So let me just run it. So in order to run a code in this source, you can directly control, you can just click on somewhere in the code, right? R is smart, so you don't have to. So this is basically one line, but I can drop it to do right. So R knows after this process is need to go to the next line. So you can go somewhere and control enter. It reads the data, and then you see here, this is my data. You can click on here and you can open the data. Okay, so you can see the variables here in each column. Is the variable name is in the first row. Each case is in each row. So each row represents one school. So this is a school number. This is a district number, API score, API 99. So this is 2000. This is 99. This average student performance. score that they assess. This is the growth, the difference between these two. This is the percentage of a student who have who are in the meal program. This is some sort of social economy status of that score. And you have all this data. All this data you see is related to each score, right? Variable are in the column, and you can look at the class of D in R. All things, everything is going to be here is object. So you can run it. Class is a data frame class, right? You can look at the variable names using names. You can look at the dimension of the data using dimension D. That will gives you the dimension of the data. So you have 400 row, 24 columns. You can look at the structure of the data. What type of variable is? This is integer. This one is numeric. So numeric has digit. Integer doesn't have any digit, right? So you can see this data has all integer and numeric. You can look at the summary of the data to get the summary statistics: minimum value, first quantile, median, mean, third quantile, maximum. So it gives you 5 number summary basically, plus the mean. And you can use help to see, for example, help of the summary. You can use help here to get the help, and you will see the help in the help panel. You can make it larger so you can read about this function, which is summary, for example. Our focus is function LM or linear model. You can also use question mark LM to get the help. This is the same as the help LM. So you will see the help file for LM function. As you see here, the first argument is formula. So formula of the linear model that you want to run. And then you have data, you have subset, weight, other argument that we are not going to cover all of them in this workshop. There is a lot of things. We are going over this, how to type the formula, and you can just add the data as a data frame. I just go over this help file very quick. In every help file in R, you see the way that you can use that function. You will see argument, which is the parameter of the function, or input of the function. If the input is like equal to true, the default is true, for example. So default is true, right, for this, for example, argument. And then you will see some detail about that function. And the value is the outcome for that function, how the outcome is going to be. The value returned is an object of class LM. And then there is more explanation about that function. There are related function to that function. So you see that Anova is related to the LM. And there is summary.lm. Is the summary, but it's not summary of the data frame, summary of the LM function. And you will see all these other function that can be used with the LM object. And you will see some examples. Okay, so this is basically the structure of all the R help files. So for now, since we read the data, let's run the model that we are interested in. The model we have is simple regression model. Dependent variable is API, the performance score, and independent variable is enroll. if we run this model, so I can click over everything, this doesn't work, right? If I run this, it's going to give me error because there is no object A here, right? So in a Stata that will work, but not in R. In R, but you can just click mouse somewhere. I usually put the end of the code and then Control Enter and run it, right? So now you see there is a object appears here, is list of 12. It is my linear result. I can look at the class again. It's a good idea to always look at the class, the model one, sorry. LM is a function. You see, there is a class also for even for the function. So class M1 is LM. So the model is LM model. You can print it and get the coefficient. And then you can use the summary to see more detail of it. So let me go back again one more time to the slide. So we read the data. The data is 400 by 24. We look at some data explanatory, and these are the descriptive. Usually with any data, you have a code book, so you know what variable means what. So a school number is a school number. Discrete number. Hopefully this school number is unique, right? So you don't have repeated for each school. In regression model, we have one observation for one individual. We don't get repeated measure for now, but we might in more advanced regression model, we can deal with that too, but not here. We have one observation for each object, right? So we have for each school number, we have one row. And then there is a school performance. In 2000, you have the growth. Meal is the percentage. English language learners is the percentage of English language learners in that school. And then you can see whether or not the school is year-round school. This is 0, 1 variable. And then you will see all these average class size of K3. So it's from first grade to K3. I think this is the same. I type it 2 times. And this is average class size for 4 to 6th grade. And you will see all this information about this data set. So in first model, we run this model. Now, the result, when we print the model, you can just type M1 and just click, it gives the print. You will see there is an intercept and there is enroll. Whatever under this enroll is your slope of the model. So basically your model is going to be something like this. So this is the intercept part and this is the slope part. It's about -2. So how to interpret that? Let's start with the slope. A slope means for every unit increase of the number of enrollments, we expect on average. So again, this is the average number of the outcome. We predict the average for a given value of the X, right? So on average, the outcome decreases by 0.2. Okay, so for example, if we want to make sense more about this, if there is a school of 600 students compared to another school with 500 students, we expect on average the performance of this school with 500 students be 20 score more, or a school with 600 students expected to have AP score 20 units less than a school with 500. Okay, so because the relationship is negative. So if you go from 600 to 500, you expect to have a positive, a more score, right? Or if you go from 500 to 600, the performance decreases by 20 units. The constant value here, again, if you go back to the linear function, intercept is expected outcome for when x is 0. So this is expected score when you have 0 enrollment. That really doesn't make sense, right? We don't have any school with 0 enrollment, 0 student. So usually when you run a regression model, most of the time intercept is not, you cannot basically interpret that result for intercept, right? So you don't interpret this. But there is a way to interpret the intercept. Right. You can see the chat also. And again, one more time, this slope is constant for any number of enrollment, right? So that value will be the same. If we look at the summary of the model, we get the more result, right? There is more than the print only. Now we see the intercept and a slope, and we have residuals here, which is 5-number summary. We have the formula of the model. I'm not sure I talk about the formula. In the linear model, when we run the model, the formula is in this way. There is a sign tilde. The response variable is always in the left side, and the predictors are in the right side. So we want to predict API 00 using enroll, right? So there is like an equation, but in the left side, there is only one variable. Okay, and then comma data equal to D. And remember, in R, we don't have API here, right? There is no object API. If I type API 00, it says this object not found. But if I say $, API 00, then I get the list of API, right? So when I run the linear model, when I say data equal to D, R understand it needs to go to this data frame and find this Y and this X, right? So if I don't do that, and I have another API in the workspace, which is where all the variables are, then I might get different results. So be careful. So it's always better to have a data like this and then variable names here. So now, let's go to the summary. So again, in the summary, we have more information. We have the summary statistics of residual. These are the observed minus predicted value using this model. What is the predicted value? Predicted value is for every X or for every enroll. We can use this formula, intercept minus this value times enroll, you get the predicted value. And you have a standard error for this parameter, estimated parameter. This is standard error for intercept. This is a standard error for a slope. And you get the t-value. So this estimated value divided by a standard error is your t-value or z-value. But t-value is approximately z if the degrees of freedom of t gets closer and closer to infinity. What is the degrees of freedom is here. This is the degrees of freedom of this t distribution. And then you get the significant or p-value, or this, basically they say the significant level, right? So here, what that tells us, this tells whether or not this value is equal to 0. Is it likely that value to be equal to 0? Is very unlikely. Or is there, based on the data, there is a strong evidence that the true error is not 0, right? But true parameter is a fixed number. We try to estimate using this data. So there is an unknown parameter as intercept that we try to estimate. When we estimate that value, the amount of error around that, if all the assumption for the model is true, is this much. So it's very unlikely that to be 0, right? In the parentheses here, we had a workshop about the significance and the do or do not say when we want to talk about significant level. So if you're interested, please go and find that seminar. We will send the video of that seminar and we present that seminar, so you can watch it. I'm not sure the slides is available. Is somewhere, but he can send you the slide. And he has a very nice talk about the significant and what you should talk when you want to present and when you want to talk about that significant. What should you say and what you should not say? Okay, and the stats is beyond this seminar. So basically, this is a p-value for the test statistic. This one tests whether or not, again, this value is equal to 0, right? As you see, the significant also for this is very highly significant, right? So based on our data, again, if all the assumptions are true, we think that the enrollment is very much related to API. API is very much related to enrollment. There is a strong relationship. Yes, we will see that in the second confidence interval. Here also you see this residual standard error. This is residual standard error. This is estimated value for that sigma, right? A standard error. And this is the degrees of freedom. You get the multiple R square and then adjusted R square. This is the R square that we talk about that. This is the percentage of the error that can be explained by the model. This adjusted R square is adjusted for number of predictors. Every time you add a predictor to the model, you get a better prediction. That's always true. So this value adjusts for that, how many predictors you add to the model. F statistics here is 44.83. Okay. For this simple regression, this value is equal to this value square. If you square minus 6.695, you get this value. Okay, but that's not always true. This is only true for simple regression model when you have only one predictor. And you will see the p-value for overall. This is the test for overall significance of the overall model. Basically, they test the model versus the model with intercept only. So this test the current model versus intercept only model. So that's for that test. The p-value is here for that test. As you see, because we have only one predictor, this value and this value are exactly equal. So these two are exactly equal. These two tests are exactly equal for simple regression, not for multiple regression. Okay, so for multiple regression, this value is different than this. It's overall test. So I talk about those things that I already talked about here. If we get the correlation between those two variables, x and y, and square it, we get the R squared. This is true only for simple regression model, again, because we have only one predictor. So if I calculate correlation using function COR in R and square it, I get this. You can try it yourself. We will do an example after this. Again, LM result is the object LM. If you want to see what else is there, that's not L. The summary is not all. You can use LSM1 and you can extract more information from that object linear model. The object was class LM, remember? So if I do LS, I get all these values. And then, for example, I can do this. You know, all of these can be extracted using $sign. List, all the elements of a list can be extracted in R using $sign. So I can do M1, which is the model, linear model object, $sign coefficient, I get the coefficients. I get the fitted values. I get all the fitted values. This will gives me 400 fitted value, 400 what I had. But I wanted only for 1 to 10, the first 10th predicted value. These are the point in the line, remember that. So if I do the residuals, I can store the residuals, all these EI. Remember, residual were EI. I can get all of those residuals and store in residuals. I can do coefficient M1 also function. This is exactly the same as this. I can do confint. Confint gives me the intercept and it gives me confidence interval of the coefficients. This is how you get the confidence interval. You ask that Claire Chu asked that. So this is how you get the confidence interval for that coefficient. Basically, these two values are, if you go back to the summary, is this value plus minus approximately 1.96 times this. That gives you that confidence interval, approximately, because 1.96 is the Z value. I have to use the T 95 percentile and 0.025 percentile of T distribution with these degrees of freedom to get that. So, but this will already compute the confidence interval for you. This is the confidence interval. So remember, whenever you see the name of that variable, that predictor variable is the slope for that predictor variable. You can plot them, the scatter plot like this, API enroll, exactly like model, and then comma data, it plots it for you. And then you can do AB line, the name of the model, comma, I can just choose the color of the line. We can make the color, make the type of the line, and then you can plot the line in the model. There is a seminar we have in ggplot that you can make nice plots in R. So our concern here is not, or you can use ggplot and make all these plots pretty. This is just a base plot in R. So, and also I added some text. You can add text to the plot for each point. I added text for X value. I add this 20 because I don't want to, I just added a little upper to the point, right? I added 20 up. So this is the basically X-axis. This is Y-axis of the point. And this is the label of that text. And this is the size of that text. You can just add the text for each. As you see, some of the points are far away from the line, right? So we will discuss that also in the regression diagnostics. And again, I add the line. So we talk about how we can extract the sum of squares, right? In R, you can use Anova of the model to get the analysis of Y variance table. Basically, the sum of squares, right? Okay, what are those? This is the sum of squares explained by the model. This is the remaining sum of squares. And if you add these together, you get total sum of squares. Okay, this is the degrees of freedom. Our model has, this enroll has 1 degree of freedom, right? This is 1 degree of freedom for this one, for these predictors. This is the degrees of freedom of residuals. The total degrees of freedom of the model for intercept only is 399, which is sample size minus 1, right? Degrees of freedom of residuals is sample size minus 1 for intercept, minus 1 for slope. That's how we get this 398. This F value is exactly the same as F value we saw before. And this P value is exactly the same P value as we saw before. And is exactly equal to the P value that for the testing in a slope equal to 0. Okay. And a few slides and then we get a break, and I give you one example to run the regression model and get all these, run it and plot it and things like that. Actually, let's do the example before going to the multiple regression. So let's open R. After you read the R, do this exercise. Try to run a regression model for API as response, and fool, the variable fool is a percentage of the teacher with full credential as the predicted value. So, and we get back at 220. How about that? Like you have 4 minutes for this example. So basically you need to run a regression model. Let's call it model E example as LM, and then you can fill out the information here and get the summary and get the residual and all those. It actually is here, but this is for API 99. And plot the line to regression model and run the analysis of variance result, Anova of the model. And if you have any question, you can now ask. Is a good time to ask a question so far we have. Oh, we use API 99 as the response variable as y, and then we use variable foo as the predictor variable. So one more minute. So basically, you can go ahead and look at these codes here and just run it and get the coefficient of the model, plot the scatter plot, and plot the regression line through the points. And also get the Anova. So keep that for when we talk about the model diagnostics for non-normal data. There are different ways for that as a remedy for non-normal data, but that is very dependent on sample size. So here's the thing: if you have a large sample size, the normality assumption is not an issue. So if you have, for example, a sample size of 200, approximately all the result is correct. The normality assumption play a role on that T distribution, basically determine whether or not you have the T distribution for statistics. And that statistic is approximately T if you have large enough sample size. And large enough depends on also dimension of the data. So if you have like 2-3 predictor in the model, and you have 100 sample size of 100, if you have fairly close to normal, not very, very skewed data, then the result is fine. You can argue that approximately distribution of the coefficient is normal. But if you have a small sample, let's say we have a sample size of 20, then, and the data cannot be assumed to have a normal distribution, then you might consider something like bootstrap. Okay, let's go over this example quickly. So for this example, my model is model example, and I run this model using API 99 as the response and full as predictor, and data is D. So I get the data, I get the model, right? So I can get the print of the model, ME, and then you can just run, you get the coefficient of the model, right? You can do the summary of the model. And that gives you the summary of the model. So you see the intercept is significant. And also the intercept is the performance if you don't have any credential teacher. The number of credential teacher is 0. So, and this is this value is the performance of a student on average increases by this much. If you add one more, the percentage of teacher with credential increases by 1%. Wow, this is great, right? And it's significant. And look at the R square for this model. It's higher than the other one, right? It's 0.32, which is not bad. This is the significance of this is adjusted R square. We can plot the line like this. And we get the scatter plot, right? It's not always pretty. Remember, the full was up to 100, right? 100% credential, and you have less. So, but we don't care about distribution of predictor. What we care is the distribution of the outcome, or distribution of, actually, to saying more precise, distribution of residual. Okay. And then we can include the line to the model. Right? This is the regression model. Okay. That's it. And then you can do Anova ME to get the analysis of variance using the regression. So you can see there is a relationship between Anova and regression. It's basically the same thing, right? Regression is the same thing as Anova. Anova, usually we learn it first for when you have a categorical predictor, one categorical predictor and a continuous outcome. Okay. So that was for simple regression model, or single predictor. Multiple regression. Now, we can easily add more predictor variable to the regression model. Basically, we can, for example, if we had enroll only, we can add more variable to see if adding these variables can improve our model, right? Can increase R square. If you add, you can just do using plus, simple plus, by adding as many as variable as you want. But be careful. Every time you add a variable to the model, you're adding one or more than one parameter to the model, right? So this is very critical, especially if your predictor is a categorical predictor with multiple level, right? So we have, for example, if you have a categorical variable with 5 categories, every time we add that categorical variable to the model, we are adding 4 extra. We will see that at the end of this seminar. We add basically 4 extra parameter to the model to estimate. Usually, if we have a small sample or moderate sample, for about like 15 to 20 a sample, we can estimate 1 parameter. So if you have, at least you need about 20 sample for simple regression. If you want to add another variable to the model, you need something like 30 to 40 sample at least, right? So be careful, it's not a good idea always adding more variable to the model. And sometimes that variable is not related to the model and is basically make your model specified, okay? So here I'm adding these 2 variables, and look, before enroll was significant, now the significance is different, right? Is not as strong as before. And also full also now is not as strong as before, but meal is very strongly significant, has a strong significant effect on the outcome. So why is that? What happened when we add multiple variables to the model? Basically, when we add extra variables, extra predictor to the model, we are estimating the effect of previous variable. For example, each variable given other variable are constant or fixed. So this is effect of enrollment when meal and food is constant, doesn't change, right? So you control for other variable and you find the effect of one variable. Before, the effect was for just comparing any 2 schools with different number of enrollment. Now, this is effect of enrollment for schools with the same meals and the same percentage of food, or percentage of teachers with full credentials. So you fix that, right? You're not looking only 2 different schools with 2 different number of enrollment. You're comparing 2 schools with 2 different number of enrollment, and you fix their value of the percentage of the meal. This percentage of the meal basically kind of represent the social economy status. So you're comparing number of enrollment between two schools with the same social economy status, with the same percentage of teachers with full credentials. So we basically control for those 2 variables, right? So then we can see the effect. Sometimes when we add another variable to the model, that effect of that variable dominate effect of previous predictor to the model. And we see sometimes when we add another variable to the model, the variable that previously was significant might not be significant anymore. Here we have large enough sample size that to detect that as a small effect. But if you had a small sample size, you may or may not get the significance for this one, for example, if the effect wasn't big, right? The effect wasn't big. You can look at this estimate as the effect size also. That's a good measure for effect size. It depends on how you define the effect size. Now, in here, again, one more time, the intercept is the API performance when enroll is 0, meal is 0, and full is 0. This value is for every 1 unit increase of number of enrollment, the school performance on average decrease by 0.05 given meal and full is fixed, or given other predictor in the model is fixed. Okay, that's how you interpret the result. Residual standard error here is this now. You see that's different. Degrees of freedom is 396. Before was 398. Remember, it was 400 was our sample size. Before was 1 intercept, 1 slope. Now we have 1 intercept, 1 slope for enroll, 1 slope for meal, 1 slope for food. So we have 4 parameters, right? So it's 400 minus 4 is 396. This is the R square of the model. This is the percentage of the error of the intercept only model. Remember that can be explained by this model, by this 1, 2, 3 variables. F statistics here is not going to be what? Is not going to be this square or this square with square. F statistics is this model versus intercept only model. Okay, so again, each of T here, each of these p-value represent whether or not this estimate is equal to 0. F is overall model fit. Okay, it's basically test all these at the same time equal to 0 in a way, right? So, and now has 3 degrees of freedom. And denominator degrees of freedom is 396. So this is numerator degrees of freedom of F. This is denominator degrees of freedom of F. This is adjusted R square is adjust for 3 predictors. So if you have more predictor, adjust more. So this is kind of like how to compare models. Yeah. So again, here you have exactly the wording of that, how you can interpret the coefficient. So one unit change in the value that vary given all other variables are held constant, or they keep constant or fixed. So now, what about Anova? If you look at the Anova of this model, oh, this was the, okay, this is the Anova of the model. The Anova of the model gives you sum of a square. For example, this is sum of a square of when you add and roll. And each of these sum of a square is the additional sum of, this is sum of a square that can be explained by enroll only. This is additional sum of a square that can explain the error when you add meal to previous model. So this is additional to the model that already has enroll in. And when you add food, you are explaining this much sum of a square in addition to the sum of a square that already explained. So basically the sum of a square is additive. So you have the sum of a square of enroll, and this is additional sum of a square for meal, and this is an additional sum of a square when you add food to the model that already has enroll and meal. And the remaining is residual sum of a square that cannot be explained by the model. So if we add all of these together, we get the total sum of a square. So residual plus all of these sum squares is going to be sum of squares total, which is this, which is the basically sum of a square of yi minus y bar. So this is the sum of a square of intercept only model. So another part of this multiple regression is when we standardize the both variable and predictors. We can use a scale to standardize all the variables and run the model. Basically, this model is the same as the model before. Everything here, p-value and t-values are the same. But sometimes it's better. Sometimes if the scales of those variables are not aligned, which some of the scales are in 1000s or millions and some scales to very small, then you have a computational problem. It's a good idea to scale all the variables to have a standardized scale and then run the model. Now, when you run it like this, then the intercept you can interpret as the expected value of API scale when other variables are equal to their mean. So this one is scaled expected to be 0. So when we scale everything, when we scale both response variable and all the predictors, then this is basically 0, right? So if you don't scale the outcome, then this value is more interpretable, is the outcome when all these variables are at their means, are equal to their mean. Okay, so this is how you run the standardized regression coefficient summary. So this is how you get the stand. So in some software, you can easily get in R, you need to scale it, rescale it to standardize and run the model. Again, the R square won't change. It's going to be the same exactly. But this is the more computationally done. Okay, so with that, we basically finish our first part of this workshop. Basically, we run the model, we did the multiple regression. Now what we need to do is we need to check for the assumption that we assume for the model. Then I'm going to start the regression diagnostics on how we can check the assumption in R. So in the regression diagnostics, we go through the checking the assumption. Also, sometimes there is a problem with the data. That is not the assumption of the model, but is a problem with the data. Sometimes you have some influential point or something we know as outliers in the data. So, and we go over that. We check for homoscedasticity or equality of variance, which is one of the most important problems that we might see in regression model. If you have an equality of variance, basically the variance given a value of x, or for each I, let's say, the residuals doesn't have the same variance and the variation is not equal, then that problem might cause the over or underestimation of the standard error of the coefficient. We check for linearity. We check if we look at the issue of independence and the normality. And then at the end, we look at the multicollinearity and model specification. Some of these diagnostics are very hard. For example, independence is very hard to capture. So if there is a dependency. So our base already has some method for model diagnostic, but we also can use some of the packages in R. One package is CAR package CAR. I'm sorry, am I unmuted? Yeah. The other package is ALR3, and another package is far away. Those packages are very useful. Another package is already when you install R is package mass. That package also has some function that you can use in R. But we are going to use these packages for this section of the seminar. So if you want to install a package in R, you can use install.packages, and in parentheses, you can use quotation and name of the package. Let me share R with you. You can also go to the package and install it directly here. So I already installed those packages and they are here, but I cannot use those packages until I actually load the package to the R. Okay, so I need to install the package. It doesn't harm if you install the package 2 times. Right, so trying to load it, restarting R. Oh, it restarted. I don't want to restart R. Okay, so sometimes when you want to install a package, you have to update other packages and that reinstall R. So it basically has some other package that this package depends on those packages. So you can go ahead and run these codes, but remember in R, if you do this number before a code, that disable that code to run. You can select that part without the number and control enter and run it. Or you can delete it and just run it. Or you can copy paste it and run it here in the console. You can go ahead and install those packages. After you install the package, you can use required, or you can or couldn't find oh, okay, yeah. That's the fourth yes, that's right. So if you cannot find ALR3, that means that package is in R archive. So you can either go to the R archive and install that package, but these packages are based on some R book or some books, a statistical book. So usually when they have newer edition, they don't update the last one. So ALR4 is the same. Yes, exactly. So, oh, this one is not. I need to install all of those packages. How about there? I already installed. I don't know if I installed this. That it says. Yeah, it says that. So I can use AR4. Then I can install this last. Oh, great. It's installed the R without deleting my environment. So this is my workspace. I have this already here. Okay. After you install those packages, you can load the package. Right. You see that I want to use VIF. This is for multicollinearity. And then I can use this package also. This scatter plot metrics is in R base, so you don't have to use any other packages. And also, if you want to see whether or not what function is with which package, you can use double question and then call that function. You know, is a better search sometimes. So go back to here. So as you see, I ran this with using older version of R. Right now is 4.05. You see how fast R is going to update itself. Actually, people are updated, but they are updating R every 3-4 months. So the next version is coming in next month, actually. So first unusual point. Or outlier. There are two different type of the point in a model. Sometimes a point is outlier. We call it outlier when the residual is very large, right? So if the predicted value and the observed value are far away from each other, then we call that point outlier in the linear model. And I will show you the picture. So if, for example, in the picture, this point, this is the linear line, and you see this point is far away from the observed value. So this is the observed value, this is the predicted value, the line, right? This point also has, these points have very high value of outlier. The leverage, in other hand, is a point that is far away from other predictors. So if leverage doesn't depend on the line, it depends on the predictors. If a point is far away from other value in that predictor for the mean of that predictor, then we call that high leverage point. So how we can detect that? I will go over that and show you. The influence is whether or not, if you take away that observation from, whether if you take that point from the data, taking away that point influence the coefficient of the model a lot. So is the amount of influence that has each point when you take that point out of the model and run the model again without that point. So sometimes if you take one point out of the model, for example, if a point is in the model, is in the line, if you take that point, still you get this kind, the coefficient is going to be almost the same. So if you estimate the model using the data without that point, then you might not change the estimated coefficient. But if the estimated coefficient change a lot, that means that point is a high influence. Basically, if a point is high in outlier and is a high leverage, then has high influence. So you can see influence as the multiplication of outlier and leverage. So to detect whether or not a point is outlier, you can studentize residual or a standard studentize the residual. This is the base, our base. And then you can plot those points and compare it to the line minus 3.5 and 3.5. Remember, we assume the error has a normal distribution. If we standardize the residuals, then we call that studentized. Then this point, pretty much they have a standardized normal distribution. If a point is here, that means this value, the error is very high, right? These are high, but it's not that bad. So you expect that value to be between -3 and 3, right? This is the -3 and 3. -3 and 3 is like the coverage of -3 is more than 99% of the data are standardized normal. So if the point is within these 2 points, then you don't consider that point as outlier. If it's outside, then you might, this is the potential outlier. So that means that might be some error or might be some unusual data point. Okay. But that itself doesn't mean this point has a high influence to the result of the regression model. For that, we need to look at the leverage also. So this way we can print the index of that point, right? This is the index, this is that, the value of that point. However, if you take away one outlier from the model, sometimes you might have another outlier present to the model, right? So not necessarily, if you have, for example, 5 outlier, that doesn't necessarily mean all these points are outlier. For multiple outlier point, you have to correct for something we call Manfroni correction. Okay, so that's also we need to consider to adjust for Manfroni correction. If we run the outlier test, gives us the Manfroni correction of, because here we had only one outlier. Basically, the Manfroni correction is 0.05. It doesn't change. So this tests whether or not this point is outlier. Okay, so this is without Bonferroni correction. Sorry, I correct myself. This is without Bonferroni correction. This is the p-value with Bonferroni correction. Bonferroni correction is, okay, by chance, all these 400 points could be potentially outlier, right? So what is the chance of at least one of them is outlier? 1 out of 400, right? So is not necessarily that if a point is outlier, that point is really unusual. To test that, you need to look at this Bonferroni correction for that point, not this one. So basically, this is not an outlier, right? By chance, there is likely you observe some point that far from zero. That's what it means. Okay. And then there is another type of plot that you can. Now, that point was an outlier, but that means that point has high influence or not. So to look at the influence, there is another plot. It calls half normal plot, right? Detail of this reason and this plot is very mathematically complicated. I skip that. The only thing that is a visual way to see whether or not a point is influential point. So if you look at this half moon plot, basically this point number 8 and 210, if you run this, they have, this is the leverage. Okay, this is the leverage. This is the normal quantile or residuals. So this point has high leverage and high value of the residual. So it stands out basically. The point that has high influence stand out. Again, I said some is you can see the influential point as the multiplication of leverage and outlier. There is a formula for influential point. It calls the Koch distance. You compare that, it's basically a cutoff point for that influential point. So the formula for Koch distance is this 4 divided by n minus p minus 1, right? So this is the cutoff point for whether or not a Koch distance is influential. So it's a test for influential. So this is actually, if you do the plot, you get the Koch distance, right? This is the cutoff for the Koch distance. So here, the cutoff is this much. Did I Koch level? I'm not sure I plot the Koch cutoff point. Oh, yeah. Actually, when you do the Koch level cutoff point, the point with higher value of that Koch distance will be showed by the index of that point. So point number 93, point number 226, and point number 234 has high influence. So if you take those points out of the model, the coefficient result will change. As you know, like it depends on based on this cutoff value. So this is a test to say whether or not, like visually, to say whether or not these points have high influence to the point. That doesn't mean necessarily you need to throw out this point. You need to consider those points and then do the more uh, investigation to see whether or not those points are real error in the data. Okay. Another way to look at that influential point is this plot. So this plot is basically called influence plot. The code for that is influence plot. And remember, the function should, like R is case sensitive. So if this P is capital, you need to make sure that if you use the lowercase, probably you don't get the result, or you don't run this function correctly. There might be another function with the same name with lowercase. I don't know. So basically, in this function, you use the model name. Main is the name of the plot. This is the whatever you want to put under here in this plot. And you don't have to define this. You can just run the code and gives you this plot. So what that plot means, if this value is high, that means the leverage is high. Hat value is the leverage. So higher value, that means more leverage. Okay. More leverage means that point is far away from other value of the predictors. Okay. Overall predictors, like all those predictors in the model. That point is away from every other point. This value is a studentized residual, or you can think about this as a standardized residual. Okay, so if this basically y-axis shows the outlier, x-axis shows the leverage. So if a point, so this point has a low outlier but has high leverage. So leverage is high. If the outlier is small, that means this point has low influence. But this 0.93 has high influence. This 226 has high influence. This point maybe, right? This point might have high influence. So basically this one, maybe because the leverage is high, right? The circle shows how far this point is from this. I think it's a circle is proportional to code distance. So if circle is larger, the code distance is higher. So code distance for this one is lower. Yeah. 234. Probably this is 234. And then you can, when you run this plot, you get this result. So this result is sorted by, I think sorted by number, but the one that it shows to this plot. You can make the cutoff point to show more values. And you can see the code distance. This function also gives you the diagnostic plots based on those code distance, studentized Bonferroni p-values, and hat value. So leverage, Bonferroni p-value, basically this one shows up, studentized residual, and then code distance. So test of homoscedasticity. For homoscedasticity or equality of variance, this is much easier than the previous one. You can use plot of residual versus fitted value. So in y-axis, you can plot all the residuals, right? Again, this is not the actual, we don't have actual error, right? Basically, we observe some errors based on our model, and then we can look at the errors versus the fitted value. Now, based on this plot, you can see the variation of residuals is more or less constant for fitted value, for different fitted value. So it's not different much. So you don't see a huge difference between variation here and variation here, right? Again, this is not a test. It's just how you heuristically test for that inequality of variance, or test for homoscedasticity or homogeneity, so homogeneity of variance. So this looks pretty. What you're looking for here is even a spread of these errors to both sides, and you don't want any kind of fan shape, right? So if you had fan shape, sometimes you have a lower variation in the end, at the end, and the higher variation at the beginning, or otherwise. Sometimes you have lower variation at the beginning and higher variation at the end. That is a sign for inequality of variance. So we have to take care of that. Sometimes a transformation can solve this problem. Sometimes, for example, like transformation can solve this problem, but not always, okay? So there is a reason that like transformations sometimes work, but not always. So there is also different type of, you might have clustered data. So the variance in some cluster, for example, the variance in some state is high, in some state is small, something like that. In some area you have high variation, some area we have low variation. So we have to look at those kind of trend in the data. You might want to adjust for clustering, right? That's beyond this seminar, so we are not going to talk about that. But this is just a heuristic way to see whether or not you have a problem in the model. And if you have a problem, there is multi-way and to solve that. Checking for linearity. Okay. So again, one more time, going back to here, we can extract residuals, we can extract fitted value from the model, and we can plot them against each other. That way you can get this residual plot, okay? And this is just a line from 0, because in linear model, the error has 0 mean. So we just get a comparison to see where should be the mean of the errors. Linearity. So if we just do residual plot, it gives the residual versus this one. We already saw that, right? Gives you the residual versus each predictor and residual versus fitted value. Okay, just residual plots. For this, we are looking for the linearity. We are looking for some sort of curvature, right? If you have some curve form, that means for some value of the predictor, the error is positive. Somewhere the error is negative. Some other where some other part, the error is positive again. If you see something like that, probably the relationship is not linear. You might have some sort of quadratic relationship. So you can see that relationship for that relationship of the outcome with each of the variables separately using this plot. So for example, somehow maybe a little curvature, but it's not that bad. It's very good, actually. This one is very good. This one is very good. The variation, remember, the residual versus fit is enough for equality of the variance. So we don't care. We don't look at the equality of variance looking at this one. We should look at this one versus fitted value, right? So that's for the linearity. So we don't want to see any sort of like a trend, like a unlinear shape here. So that's for linearity. And there is a test. If you run this code, it gives you already result of this test. This test is test of each value linear model versus a quadratic form. Okay, so it does that for you. And then is the overall test of curvature. So that's the test for curvature. So this is the test statistics, and this is the p-value. So you see all these p-values are bigger than, is large. So there is not much evidence for curvature or nonlinear relationship in this data. So the relationship is pretty much linear. Again, we are limited to this data set. This is random, right? There are always randomness. These tests are not definite tests, significant, non-significant. We are limited to what we have, right? The observation. So if we take a random sample, we might have some linear, nonlinear relationship, and then we say, oh, there is a nonlinear. No. Result of this test is not definite answer. It just gives us insight about the relationships. Okay. For independence, we can, this test is not, it's very hard to see the dependency. But if we test a residual versus the number of schools, I'm not sure, but this is somehow you get some sort of, if there is a trend here, then that means one school, it depends on the other school. Like some schools that have the same numbers maybe has lower residual. Some other schools have higher residual. So residual of one school is depends on the other schools. You don't see those kind of trends here. I'm not sure this is the best way to see the independence. The test of independence is very hard. The last one of this set of the diagnostic is normality. Usually you don't see that pretty normal form here. This is very normal. Again, when we test the normality, this is one sample of residuals, is not actual error. We are testing residuals, right? Residuals based on the model. We hope this residual represents the error, the actual error from the model, the actual unknown errors from the model. This residual depends on the data. Okay, so we can do QQ normal plot. So basically, QQ normal plot is quantile of theoretical, which is the normal, versus quantiles of the observation. So here, basically, the residuals are sorted from lower to higher. So this is basically percentage of less than this value. Percentage of the data less than this value, that gives you basically the sample quantiles. And then theoretical quantile is basically probability of getting a value less than this, right? So it gives you that value. So, or you can think about this theoretical quantile as if you randomly sample from a standardized normal and sort it, that would be the case. So again, this is the value of the normal for, if you have, for example, 400 sample, is what value of the normal distribution has probability less than that value is 1 over 400. What value of the normal distribution probability is 2 divided by 400. So, and then you can plot this against each other, you get this quantile versus quantile plot. If is a line, that means if the residuals are pretty much normal. Again, for normality, as long as this data is not crazy non-normal, then I don't care about this normality, because the sample size is large. So there is a trade-off between that. So let me so let's say if I had something like this, then I would be worried if a data was like this. But if the data was something like this, I wouldn't be worried much because I have enough sample size. So that is based on experience, and also sample size is very important. Sometimes your data is the outcome variable is not distributed as normal, so it's continuous, but for example, it's a Poisson distribution. So in that case, there is a different method for running that regression. For example, we call it Kant model, and that will take, because of the Poisson model, the mean and standard error are equal for each given value of the mean. Then, of course, the standard error is not going to be equal. Then you need to run it through some different method. For example, you can run it through a Poisson model. So somebody asked that before. So that one way to run the outcome variable, which is not. So again, let me, in parentheses, I tell you something. With no mean, we claim that we can cover linear model in this workshop. Linear model is a maybe 1 year course. So you have to take like linear model 1, 2, 3 in 3 quarters to cover. Maybe you can be able to cover everything in linear model. So please understand that this is just a basic idea for some researchers. They want to have some sort of idea, and they don't want to sit in the class for a whole quarter to learn linear model. So it gives you some insight about the linear model, and how to run it in R and what is there. But with no means we can cover every aspect of linear model. There is a lot more in the linear model. So there is another thing that is important. Sometimes two predictors are very highly correlated with each other. If two predictors exactly correlated with correlation 1, when you run the model, you get the error of singularity. The model even cannot estimate the parameters. But sometimes you have very highly correlated predictors. In that case, the model is not stable in a sense that the standard error might be extremely high and non-reasonable. So again, every time you add a variable to the model, you make the model more complicated, right? So you add and you need to estimate one parameter. But that's not it. Sometimes two variables are highly correlated. Then that high correlation makes the model unstable. So that high correlation makes the residual standard error very high. And if the residual standard error is high, the estimated residual standard error, then the coefficient standard error is inflated. And you have to be careful. So basically, the estimated value for that. So for example, if I tell you the slope is 10, but a standard error for the slope is 50, that means the slope is from minus 40 to with very high chance, the slope minus 40 is acceptable, right? You cannot say this is unlikely. You very much likely get this. So it's not informative. So in that case, you want to reduce this collinear, basically, which is high value of the standard error. To test for multicollinearity, there is a function in the package car that we use is VIF. So if you run VIF of the model, again, if in particular, sometimes when you have multiple package in R and you want to run a function in one package, that function might exist in another package. So in order to make sure that function is from that package, you can use this colon and colon. You can use car colon colon VIF. VIF gives you the some sort of indices to tell you whether or not that value is that variable is collinear with other variable. So they call it variance inflation factor. Basically, we don't go over the formula for that VIF, but the good thing is this VIF is only depends on predictors. It's a measure of correlation between these predictors. So that's good because, for example, if you are running a Poisson regression model, right? You can first run the model using linear model and use VIF to get the multicollinearity of predictors, because the multicollinearity doesn't relate on the outcome variable, right? So, and then you can use that that for testing multicollinearity. The cutoff for this multicollinearity is usually 10, right? So if you have a value more than 10, that means that variable is highly correlated with other variable. So you can drop that variable from there. It's not appropriate to use that variable to the model. So you might consider that. Model specification, whether or not a variable is useful in the model. So you can use this added variable plot to basically plot the relationship between that variable to the model. If the linearity is not very strong and this line is close to a horizontal line, that means that variable is this is kind of like a significant test, but is just sort of like this variable is highly appropriate to add to the model. Maybe this one, you can just test that. And it's called added value. In the old time, they use a lot of that, but right now you can use the model selection, forward, backward, or forward and backward at the same time. Model selection, select the variable that are appropriate to the model. With that, we finished this part of the seminar, and the last part is going to be regression with categorical data. If we go to here, you can click on this to the regression with categorical predictors. I go over this part very fast. The reason is there is a lot more in the regression with categorical variable, and also the part that we haven't covered in this seminar is a regression model when we have interaction between categorical with categorical, categorical continuous, continuous with continuous. For that, I strongly suggest to go to this seminar. If you go to R and classes and seminar, this seminar, decomposing, probing, and plotting interaction in R, goes over all different type of interaction, how you can extract the interaction in the data. So this is very helpful. And using a package, a very helpful package called EM-means, and you can plot the interaction. So again, as I said, there is many, many more things in the regression that we are not able to cover in this short time. So when we have a categorical data, for example, categorical data might be 0 and 1, two-level category. In R, a categorical variable is actually, in R, a categorical variable can be shown by a factor, right? So here's the thing. If you don't use factor and you have a three-level category and that variable is 1, 2, 3, or use that variable as a continuous variable. If you have a variable which is integer and that variable is 0 and 1, or it doesn't really matter to use that variable as factor or integer, because the way that R treats that variable is basically the same. Okay. But if you use R, if you want to use a categorical variable, it's suggested to use a factor for that variable. So again, every subject in R has a class. So API is integer, for example, right? Integer is number. For example, year run is also integer. And this one also is integer, right? Meal category, class of meal as categorical. But if you look at this variable, right, the summary, the mean is 0, the max is 1 for year run. These variables tells us whether or not the school is year run the school. So the mean is basically the percentage of the year round school in the data. So 20% of the school is year round school. If you look at this variable, you have mean 1 is not very usual. The max is 3. There is a median 2. There is a first quantile 1, right? So if you look at this variable and you look at the table, you can see that there are, for example, year round, there is 308 schools are 0, and there is 92 schools are 1. And if you look at this one, you can see the mean is categorized already in the data, right? So this variable is a categorical variable in 3 categories. Sometimes the category is ordinal. We can still treat that categorical variable as a continuous predictor. But if it's not ordinal, it doesn't make sense to run a linear model through that categorical variable. So instead, okay, this is also the percentage of the meal, right? This is how they categorize. So if the 0 to 46% of a student gets free meals, that means the category is 1. If 48 to 80% gets free meals, the category is 2. If 81 to 100% of a student gets free meal, the category is 3. So this is the use K again. So basically, this is if you think about this free meal as a social economy status, so these schools have in the lower social economy status than this part, right? So in R, you can use a factor. So I created a factor for this variable. So if you use factor, this variable becomes a factor. If you look at the class, it gives you the factor. That means this variable is a categorical variable, has different levels. If you do levels of the class, gives you 0 and 1, which is the levels of that factor. So a lot of you might know already factor, but this is how you can treat the categorical variable in a regression model. So first you make it as factor, and each factor is each level of that factor is each level of that category. So now this variable is not 0 and 1, so you cannot just add that variable all together. If you do the summary, all of a sudden, instead of getting the 5-number summary and the mean, you get the table summary of that variable. And the summary gives you the table summary. Because R look at this variable, and because this variable is factor, then it treats it as a categorical, and it gives you the table based or frequency of each variable, but each level. Now, let's run the regression model using this year run. If I run this model, again, same as before, I get the intercept and slope. I get R square, I get everything else. But the only difference here is this. The way we interpret this estimated value is different than continuous variable. In here, we have two levels, right? One level is 0 where the school is not year round. One is when a school is year round, right? So this factor, when it's 1, you can see when the school year is yes, run, right? So intercept here, again, like when we had the continuous, is when x is 0, right? When x is 0, that means you are in the class of the schools that are not year-round, right? So basically, this is expected average of a score of the school when the school, given that a school is not year-round. So on average, we expect that the mean of a score for performance is to be 684.55, given that a school is not year-round. This value is the difference between this and this. Basically, this is, if you add this plus this, you get the average of the school year. You get the average of the API score when a school is year-round. So this plus this. This value is the difference of the performance of a school between whether or not a school year is run. Between a school year is run and a school year is not run. Okay, so if you look at the formula, right? So you have intercept and a slope, right? I think year round. This is coefficient. Okay, B, I mean by B is the coefficient of year round, right? And this is the variable, is 0 or 1, right? So if you put the value 0 here, you get the mean of when a school, right? 0 times this, 0, you get the intercept. Is the average of the school performance when a school is not year-round. When you put value equal to 1 and you multiply by this, if the school year-round is 1, then you get the average for the school year run. This value is the average performance of a school when a school is year-round. Make sense? So if we plot this model, you see the model is discrete, right? You have either 0 or 1. And AB line is from the average of year goes to average of year. And you see that when a school goes from 0 to 1, the average performance decreases. So basically the difference, this is basically the slope kind of, but is not really a slope, is the difference between the mean of here and here. So if you just do the mean of all the schools when year school is run, you get, when year school is run, you get this average, you get this value. Exactly the same, right? And this is the value exactly for this one. Right. What you don't get using the average is this standard error. You can get the standard error of the predicted mean using this model. And this is basically testing whether or not the difference between, this is basically the same kind of as the t-test, right? This is basically the same as t-test of the difference between two scores, but a little bit different because it depends on how you treat the standard error. If do you assume the standard error is equal or unequal? So if you assume the variance is equal, the test statistics, I think, is exactly the same as linear model, 10.782. Here also you get 10.7. Right? So because this standard error assume that the residual standard error basically assume the two group has the same standard error. Okay, you can again use the Anova. Anova is the traditional Anova that we had, like a treatment and the sum of a square of treatment, sum of a square of total, sum of a square of error is the same. Here is the sum of a square of treatment. This is sum of a square of residual, and the additional these two is sum of square of total. And again, if you square this, you get the F statistic. Now, if we have multi-category predictors and you use the variable as the factor, like meal category as factor, or take the first level, if you do levels, the first level is going to be the reference group, right? So meal category F1 is going to be the reference group when meal category is 1. And then compares these groups to the reference group. So basically, this is the school performance on average, expected school performance. When the meal category is in category 1, this is the difference of the school performance of meal category 2 to meal category 1. And this is the school performance of meal category 3 to meal category 1. So this is how you can run the model. This is only when you have one. So again, this part I skip quick. We don't have much time. You can aggregate the mean of each category and compare these values to this. So basically, this value minus 1.66 is the difference between 639 minus 505. You get this value. And then the difference between this and the reference group is this difference. So this test whether or not this group is different than reference group. This test whether or not this group is different than reference group. And then overall test is test whether or not overall categorical variable has significant effect on the outcome. So basically test these two at the same, the difference at the same time. You can re-level the categorical variable and then run the model level. Now this model has category 3 as reference group and compare other two category to category 3. So this way you can just change the reference group and get the difference between F1 and F3. So the reference group is when the social economy, the percentage of a student who gets the meal is more than 80%, or who apply for the meal. So you see the category group 3 is omitted. That one is the reference group. And with that, we finished this seminar.